like makes me like see. Okay, guys, let's get started. I have a handout today, yellow handout, 2 stacks, same thing. We got the purple outline, and we got the white handwritten. How's everybody today? Just Danny. This side of the room is a little heavier. Lab this week, we're doing bromination of transtylbene. It went pretty well yesterday. Reacting an alkene with elemental bromine, Br2. We'll cover that reaction today.
Free coffee day or no? It is. Right? I didn't realize.
Okay, guys, we can get started. The outline is here. The top reactions we've covered. Top reactions, Roman numeral 1. What's the comment with all the top reactions? They all involve a carbocation intermediate, right? Today we'll be moving down to Roman numeral 2, down below. More reactions of alkenes, lots more. Very interesting, unique reactions. Alkenes, very versatile. These do not involve a carbocation intermediate. Because of that, these are not prone to rearrangement. Basically, they do not rearrange. You will see no rearrangement for these. You only get rearrangement when you form the carbocation. All right? We'll probably start right here and go around. So right here, the first thing is we'll react this with X2, X typically being halogen. Most common is chlorine, Cl2, and bromine, Br2. Real briefly, X2, we're going to add the 2 halogens across the pi bond. That is 1 halogen to this carbon, 1 halogen to that carbon. Because halogens are the same, we don't have to choose which one's going to get a halogen. They're both going to get a halogen. So there's no regiochemistry to consider. Put X here and X here. But importantly, and in most all of these reactions down here, we're going to have to consider stereochemistry. And as we move along, we're going to do more and more stereochemistry. So, we'll start here. We may go back before we actually begin. And so the outline on the other page there, we would be down with B. Electrophilic conditions without a carbocation intermediate. And the first one is the trans addition of halogen. This is addition of halogen. Okay, elemental halogen, X2. And it indeed occurs by a trans addition. You'll see what that means. It can also be interhalogen, ICL, etc. Okay, before we get to that, were there any questions about what we've covered thus far? Any questions? Question?
Can you go over ring contraction again?
Ring contraction. There was one mechanism to do. This one here, going 7 ring to the 6-membered ring. How are we doing that mechanism? Who thinks they had a pretty good shot at it? Got the mechanism. Anybody? Yeah? Pretty good. First step is, well, all we know is pi bond reacting with H plus. We got a pi bond, we got H plus, right? I mean, this is H plus in water. We can show that H plus. We come back over here. We need this 6-membered ring. If we can somehow get that carbocation, can you make it home from there? Water attacks it, and then you lose an H from the oxygen to go neutral. So how can we get that? This is a carbon with 2 methyls on it. You got this carbon with 2 methyls on it up there. It's almost like somehow we want to get the carbocation there. But originally it's either going to be here or here, right? But if it's here, maybe we can somehow do a hydride shift or something to get it here. So I'm going to make the cation be up there first, because either way is secondary. Top or bottom, either way is secondary, but I'm going to put it on top. So I'm going to hinge down from here and make bond to here, and I'm going to get, what is it, 7-membered ring? That should be 7. With new H there and a carbocation there. Now at this point, I'm only one arrow movement away from that over there. What do I need to do to go from here to here? This bond here, I'm going to break it away from that carbon and go bond it to that carbon. It looks like it's long distance. Okay? But really, this ring can pucker up a little bit. Break it away from that carbon and bond it over there. Okay? You got to envision this. This is bonded here. I'm going to pull it down and make it bond over there. I'll draw it just like this. Boom, boom. So instead of bonding here, I'm going to not bond it there. These are electrons. These electrons, instead, I'm going to bond them over here. Okay? Well, now that's a 6-membered ring. But what is up here now? That carbon lost the bond, so what is that? Positive. And what is that? That's that right there, just redrawn with a nice 6-membered ring. So these electrons moving here led to a ring contraction, new carbocation. This is secondary. It's also a big ring with open angles. Now we got tertiary with a better ring size. That's going to be favored. How do we get home? Water. These electrons do what? Right there. That's going to give 6-membered ring. Oxygen there. The oxygen has got 2 H's. 1 lone pair left. That's a plus charge. How do we get final product? Something has to take the H. Water can remake that, or there's got to be a minus here. Okay? Maybe this was aqueous sulfuric acid and you got this minus. Water certainly is fine, or you could use this. I wouldn't even draw the Lewis structure. Take the H, these electrons stay behind as the second lone pair. You make that and you reform your acid. Of course, how does that exist in water? H3O+. Either way you want to do it. I don't usually draw out the Lewis structure for this and show the electrons. Or you can use water. How we do? You got to be working on envisioning your mechanisms, envisioning what bonds need to be. And it's basic principles. Not much new. That's what we've been doing for the last 2 days.
With hydration of alkanes, in the notes it says that the acid catalyst, for examples, it says H2SO4, H3 phosphate, but then it also says HF.
HF.
Does that not fall under a halogen?
No, HF, F minus does not attack the carbocation. HF can be used as an acid catalyst. F minus will not attack the carbocation in this class. Okay. How do we do on this one with the THC? Any questions about this one? What bonds do we need to form? We need to form that bond right there. Oxygen needs to bond to a carbon over here. Because right now it's not bonded to a carbon. How can we get it bonded over there? Well, the only chemistry you know right now is carbocation chemistry. The only chemistry you know right now is alkene reacting with H+. Well, that's what we got. This react with H+. Where are you going to make cation at, left or right?
Left.
Correct. So this is going to hinge down. New H here, carbocation here. I'm just going to cut that off. Can't cut it off too much. Let's see. Boom, boom. That's that up there. What can attack carbocation? We can have some nucleophile externally, but right here we got an internal nucleophile. These electrons, bam, right there. Internal nucleophile to make a ring. What does that give? Well, it's going to give that right there. Oxygen is going to bond to that carbon with two methyls coming off. Okay, here's one methyl, here's another methyl. See, that's a methyl. It just has, there's three H's there. One of them's drawn in. You'll have the structure with an H here. I'm not going to do it. Right? That'll be plus. That arrow gives this. And then something has to take the H and leave the lone pair behind and give you your final product. So this is just a intramolecular nucleophilic addition to a carbocation. Question?
Since H plus was a catalyst, does something have to take place?
H plus is the catalyst. Something would reform the H plus. There's got to be a minus here. You can't go to the stockroom and just get H plus. You got to get a minus too. What acid do you want to use here?
Water.
Water's not an acid.
H2SO4.
H2SO4. Okay, that means the minus would be HSO4 minus. You could use that to take the H, get your final product, and reform sulfuric acid, which is an acid, which is what you need to start with, the H plus part of the acid. Okay, so that's just an example of an internal nucleophile. Nothing really new there, other than the internal part. But we did one of those before, didn't we? Yeah.
So will carbons be given to an internal nucleophile all the time over an external nucleophile?
Yeah, internal's always faster. Clap my hand. Beat you to it. See? Try to get it. Sorry. Internal's always faster, right? Today and the next semester we're getting two. Okay, guys, I think we're ready to move on to new reactions. Letter B, transition of halogen. This is on the handout. Next page, up here. Typically, this is just elemental chlorine or bromine. Fluorine is too exothermic, too dangerous, explosive. Iodine it's endothermic. It doesn't react. It won't go forward. Bromine, chlorine, good. Okay. Here we go. We have pi bond. These electrons are a source of reactivity. Cl2. Okay, first off, Cl2 is covalent. You do not want to show Cl plus, Cl minus. It's not ionic. Now, it seems like there's no dipole here. There's not a permanent dipole. Your halogens, though, are sort of schizophrenic. They sort of pull on each other and create temporary dipoles. Halogens are known to be polarizable. You can look that up tonight when you get home on the internet. Polarizable. Basically, we can get this sort of fleeting dipoles, even though it looks like there's no difference in electronegativity. This chlorine gets mad, starts pulling, leaving that one positive. So at that point, the electrons attack the positive. Now, down here, just like before, we're going to make plus on left or right. Make it on the left, correct. So these hinge away from the left and go make bond to chlorine. There's my arrow. As they make bond to chlorine, something has to leave. These electrons leave. So we're attacking one atom and the electrons are leaving at the same time. We didn't form Cl plus, like H plus. But that would give this structure down here, this carbocation. On the left. Okay. Now, what did this arrow right here do? That broke the bond, electrons moved on to chlorine as the fourth lone pair, and that formed Cl minus. Now we got a plus and we got a minus. The minus can be attracted there, and if that added there, we would get the final product. Halogen on each carbon. But what do we know? Which is going to be faster? Chlorine internal or the external? Internal. Internal. See, the new thing we added has a lone pair. It's going to bond faster than A. A bonded, we'd go that route. Instead, this bonds. I call this back bonding. What does this arrow mean? It means this lone pair bonds to this carbon. What does that give? It gives this structure. With that bond formed. Now at this point, this chlorine has a positive charge. Okay, you know how to determine charges. This is a three-membered ring. It is strained, but it is known to form. This is called a chloronium ion. It's a bridged three-membered ring with a chlorine, positive chlorine. Now let's go through here and then let's talk about why we're doing this. Next, the end result is to get a chlorine on each carbon of the original pi bond. The next step is that chlorine, instead of it attacking there, it's still sitting here. It then comes in here and attacks this carbon and kicks this chlorine off. We're going to call this backside attack. So what does this arrow mean? These electrons bond here. So now we got that bond there. These electrons break away, so that chlorine is no longer bonded here. These electrons move on to chlorine as the third lone pair. There's three lone pairs on the chlorine. Everything is now neutral. Both chlorines have three lone pairs. This is known to be the mechanism for adding chlorine across the pi bond. Chlorine to each carbon. Or bromine. Note, if this chlorine added here, you get the same product. But that's not the mechanism. We know that's not the mechanism because of stereochemistry outcome. We will show the stereochemistry in just a minute. Now, I'm surprised nobody's asked me. What does B say? What was underlined?
Back bond.
It says reactions without what? No carbocation. So why did I show carbocation? Why did I show this, right? Aren't we at B? And B is what? Reactions without carbocations? So why did I show this? First off, why didn't you ask me that? You say, why are you showing that? We're under B now. That's because this is not actually formed. And I'm going to write NaF. NaF means not actually formed. And you may not see this in your textbook. I'm the only one that I know of that says NaF. Other textbooks will just show you all these arrows and there you go, your chloronium. I'll show you this here because I want you to do it stepwise, even when it's not stepwise. We'll talk more about it. So really, how many intermediates are up here and going from there to there?
4. 2 intermediates.
1. Okay. There's 2, but this one's not actually formed, so that leaves us with only 1. And the only intermediate is called what? Bromonium ion. Or if you're doing bromine, it's called the Bromonium ion. That's the only intermediate.
If asked to complete something like this on a test, do you want us to show that not actually formed step?
Yeah, if you show this, you need an NaF.
So you need to write NaF.
Yeah, you need to write NaF. If you show that. Question?
So you don't have to show that though.
Okay. I'll do it like a textbook or wherever. Here we go. To get there directly, these electrons attack here, these electrons attack here, these electrons come off to get there directly. That's it. What's going on here? This attacked chlorine. At the same time, these electrons back bond, and these electrons break away. All that gives this. But I think it's just too much for the beginning student to see all these arrows like this. This also reinforces where the cation would form if it did. Because down the road, when we have a choice, this is going to attack here. We'll talk about this. Okay? You're welcome to do this. Don't show this and go straight to the chloronium. But you need to understand what every arrow means. Basically, I did the first 2 arrows there and didn't do this one. What does that give? It gives this. Then I did the back bonding to form that. But in actuality, this back bonding occurs at the same exact time as that. Okay? So 1 and 2 are actually, what do you call it when they happen at the same time? In chemistry, you call it concerted. Same time. Here we go. Help me out here. I'm the pi bond. You're chlorine. You're bonded to her over there. No bond like that. Okay. All right. You might have to lose your arm there. Okay. Electrons coming in. First off, why would I attack this chlorine? Somehow partial positive develops. Chlorine is schizophrenic. It's polarizable. Somehow you get some partial plus. She starts pulling on you and leaving you partial plus. These electrons get attracted to that. Okay? Now here, as soon as I come this way, I want you to bond over here. Yeah. Okay. Hold on, let's do it this way first. First I'm going to bond and leave a cation. Okay? But there's no real cation in this form. Because he has a lone pair. See, that's very important. The new thing that was added has a lone pair. If we added an H, it would not have a lone pair, and the H cannot back bond. As soon as I bond to you, you bond to me. Here we go. Transition state, right? Start bonding. Over there. And there we go. 3-membered ring. This never forms and waits and then the back bond. Everything happens at the same time. Attach like this. It's really like this. As soon as it starts attacking the chlorine, what are these electrons doing? They're coming this way. I just think it's too many arrows to show all together. I prefer to do it like this and say, hey guys, this is not actually formed. Let's show it anyway. I think it's easier to understand. When it back bonds, there you go. This is your only intermediate. Okay? From there, this chlorine comes in here. Now let's talk about that. Why would it attack here? Well, this is a strained ring. Chlorine is electronegative. It starts pulling here. Okay? You might say, why does it back bond? Well, it back bonds because electrons are attracted to positive. But still, it doesn't want to back bond a lot. It starts pulling. And as we pull, partial positive develops here like this. This is where the electrons are being pulled toward chlorine. Partial positive develops. Now, would you rather develop partial positive on the left or the right?
The left.
On the left. It's almost like a cation. That's where you get the most, okay? But it's not a free cation. If it was a free cation, we just would have shown that right there and we would attack chlorine, that would have been it. This back bonding is very important. And the partial positive happens at the same place you would form cation. And that's where your Cl minus attacks. Because minuses like partial pluses. And when this attacks, it just kicks these electrons completely off. And that gives you your final product. But the importance of this is this back bonding blocks this side. Okay? Review. How do you attack a carbocation?
From both sides.
Either side. Now, if this is on the wall, it's front or back. Pretend it's like this. It would be up or down. Okay? Pretend it's like this. But see, this is not a cation. And that back bonding blocks this top side. Okay? It's like, uh-oh, I'm blocked. You can't get to me. My hand's in the way. Because of that, the chlorine has to come in from the bottom. And that's what their stereochemistry's outcome is going to be in just a minute. Anytime you attack a carbocation, you attack from both sides. Whenever you attack a carbon and kick something off of that carbon, like we're doing here, you attack backside. What does backside mean? Backside really means opposite side. Opposite the side of the leaving group. The thing that leaves the carbon is called the leaving group. If it's up, the nucleophile is going to come in down. It's called backside. Okay, first let's just do regiochemistry. Regiochemistry is quite easy. Alkene, bromine, what are we going to get? You're going to get a bromine added to each carbon. Okay? Boom, 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 boom. Bromine there. Bromine there. There you go.
So on the test, if it just asks to predict the product, we can just show that.
Two types of questions. Predict the product is product. If you're asked to show a mechanism, then you need to show the mechanism. You'll be given a product. But again, whenever you're asked to give the product, I would just treat it like a math class. If you're asked to give the answer to some math problem, what do you usually do? You work it out by doing a formula. And here we call it our mechanism. If you don't know how to do mechanisms, you're going to basically be relying on memorization, and it may work for another couple of weeks, but then it's going to become just like math. You don't memorize all the answers in math, do you? You do? Then you're not doing it right, okay? If you will learn mechanistically, you'll be able to do everything you want, and organic 2 will be pretty straightforward. Mechanistically, what happens? This reacts with the bromine to form what? Bromonium ion. Right? These react to form bromonium ion. That there? Yeah. I mean, you can go through just like we did before I erased. How did we get there? It attacked the bromine cation here, but it's not actually formed, is it? Because as soon as the cation is formed, what does the bromine do? It back bonds, and you get to this point. You just have to go back and do it. At this point, the other Br, which became Br minus, what does it do? It's going to attack one of the carbons and kick it off. We're not attacking a carbocation. We're attacking something that, and the other atom gets kicked off. When an atom gets kicked off, we call it a what? What do we call that atom? Leaving group. Okay. Which carbon does it attack? Right or left? Over here, because this is going to strain, and we're going to get more partial plus over there, just like where we put the cation. But it's not really a cation. This attacks here. It's actually backside, but I have no stereochemistry to illustrate that. We attack here, kick that off. What does that give? Bromine bonded there. This is kicked off. This bromine just bonded there. Well, that's that. Okay? But again, in terms of just predicting the product, this is the easiest reaction to ever do in organic chemistry. You just add a bromine to each carbon. More importantly will be the stereochemistry and understanding the mechanism. Question?
So, as long as you're paying attention to the relationship between the two halogens, it doesn't matter which way you put your triangle, right? Because my triangle's like up instead of down.
It's okay. We'll learn when it's important to consider it. And on the next page, we'll start doing it. Okay? I'm easing this into it. ICl is an inner halogen. Okay? Now we have to consider which carbon gets the iodine, which carbon gets the chlorine. Okay. Well, here we have a permanent dipole. Which one's partial positive?
Iodine.
Yes, because we've got a permanent dipole. There's no schizophrenic here. Iodine is partial plus. Chlorine's more electronegative. So the electrons here attack which halogen? The iodine. So these electrons are going to be attracted to the iodine, and we're going to kick the chlorine off. The chlorine's a leaving group from the iodine. Which carbon is bonded to the iodine?
The last
The
one.
one on the end or the second one? One on the end. This is hinging out this way. Because we know we want to get a cation here in our thought process. What does that mean? Electrons move on to chlorine as a fourth lone pair. We get this. There's a plus there, but hold on. What we're going to say is anytime the new thing has a lone pair, what's it going to do? It's going to back bond immediately, and so that's not actually formed. Back bonding happens at the same time as the initial bonding. When it back bonds, what do you get? Iodonium ion. It's a bridge three-membered ring. Yes, it's strained, but we have an additional sigma bond. That makes it better. Yes, it's strained and the iodine pulls. Does it pull on the left carbon or right carbon more? Correct, because that guy has this sp3 carbon donor. The answer over there is the same as the cation. You get more plus there, so the chlorine, where does it attack? It attacks there. These electrons get moved onto the iodine, and what do you get? Iodine's out there, and what's here? There you go. There's your product. And you do not get chlorine out there and iodine here. So So because we have the two different halogens here, this inner halogen, now we have regiochemistry to predict. Yeah, chlorine's going to be there. But that product comes from just your mechanistic thought, right? If you go through the mechanism, dipole, where do we attack? That's it. You don't have to memorize that. And in fact, as soon as you memorize it, all I got to do is just tweak it a little bit, and then you won't know what to do. The goal is to not memorize it, take tests, and forget about it. The goal is to actually learn something, and when you get to the next class, be able to apply some principles. So did that make sense for this? Yes. NAF. If we did a reaction coordinate diagram, how many intermediates for this reaction? One. Only one. Okay, I've already mentioned why not F2 or I2. HI will work for hydrohalogenation, but it won't work with I2. If you do some thermodynamic calculations, you'll see that it's endothermic.
Does anything happen with the IF interhalogen?
IF?
Yeah.
I don't know that I've ever seen it. It probably exists. But you would rationalize it just like you did the ICL or whichever one. I don't know which interhalogens are common or known. They're probably all known. Okay. Important for this reaction though is stereochemistry. If you take cyclohexene reacted with chlorine, we're going to add a chlorine to each carbon. Bam. But because it's a ring, we have possibility of cis and trans. They can both be like this, cis, or they can be opposite, trans. Actually, cis, they can be both forward or both back. Trans can be back forward or forward back. Or the other way. Now let's go through this. If we attack the chlorine, kick it off, we get this with a carbocation. But we also get this one over here. Because this new carbon down here is now tetrahedral. Pull it down here. Here it's sp2 planar, but now it's tetrahedral because there is an H here. Okay, there's an undrawn H here. Undrawn H. Since it's tetrahedral, the chlorine can either be forward or back. And we show both. Now, if the cation is actually formed, when the other chlorine attacks it, is it going to attack from the front or back? How do you attack a cation?
Either side.
Either side. So if this was present and you attacked it, nothing changes down here when the top attacks. But the top would either be forward or back, right? Because the chlorine, if it attacked from the front, it'd be this. If it attacked from the back, it'd be that. So if that cation was formed, you should get both of these. And if this cation was formed, you should get both of these. Because this is back, that's constant, but the top can attack from the front or the back. So if there really was a cation, you should get all of these. Problem is, if we go do this in lab and you study the product, you do not get any of the cis. You only get trans. That means it's apparently not forming this way. Our mechanism has to account for all the observations, including the stereochemical observations. Why do we only get trans? Well, the reason we only get trans is because it's really not a cation. Because what happens at this point? That really doesn't exist, does it? What happens? And I see that I actually didn't show that up there. You had that in front of you. You only get trans. So basically I told you what I already have written here. Cis is not formed. And I explained to you there. Let's further explain why. Not shown here, I'll show it below. I'm going to pull this down so I can draw a mechanism here. From here, I'm going to say NAF. Because at this point, what happens? This back bonds. And that gives, you can draw somewhere where you got room on your paper. When that back bonds, what do you get? Now this bond is forward, and when that back bonds, this is going to have to be forward. And that's going to be plus. Same thing over here. This is not actually formed. Instead, this back bonds. Now, if that's back, this other bond is going to have to be back. When it back bonds, you'll be like this. Everybody understand why both have to be that way? Here's the plane. If we consider this planar, we know it's really like a chair shape. But if the bottom chlorine is forward, and these electrons just make a bond there, these are going to kind of just move up, okay? Pretend like that and the top of that are now bonded, okay? But they're both still forward. There's no way this bond can be this way and the other bond be that way. Same thing here. The original bond of chlorine is going back. The electrons just bond up there, and so you just now have two bonds. One to the bottom, one to the top, but they're both going back. That's not actually formed, this is formed. At this point, the other chlorine comes in. Now we can attack either one. Which one are we going to attack? It doesn't matter, it's symmetrical. But I'm going to attack the top. Now, the top, this bond is coming towards you. It's like this. And if I had another pen, I'd draw the other one. It's like that. Okay? If you can tell, three-membered ring, but they're both bonds are coming towards you. But let's focus on that one. If that's coming towards you, how does this other chlorine come in? Backside. If this bond is that way, the other one comes in behind it and kicks it off. So if this is forward, how's this going to come in?
Back.
From behind the board. Backside is truly behind the board. So this comes in backside. And since it comes in backside, we kick this off. Nothing changes here. So that's still forward. But how's the new bond here that came in? It's from the back. Because it comes in backside. And lo and behold, this is what? Not cis, but trans. You only get trans. Now you get the other one by over here. Here the bond is going back behind the wall. Since it's going behind the wall, how does this one come in?
Front.
It comes in the front. Pretend like this is the board. Okay? This chlorine's going behind the wall. This one comes in front, kicks it off. But now the new one is coming forward. I can't show it coming forward. I don't have a flame there. But we know since it came forward, that's now bolded, came in from the front. That's still there, so it's right there, and there's your product. And lo and behold, it's not cis, but trans. Two different trans products. Question?
You said that because the product, we know that it couldn't have formed a cation, but so the presence of the first bond in chlorine alone wouldn't be enough to make the second bond trans if it was a cation?
If this chlorine attacked here, you're saying this how do you attack a cation?
Both sides.
Well, you said-
Either side.
That was my question. Is that the presence of the previously bonded chlorine just wouldn't be enough to push it
Yeah,
into trans?
You could maybe try to argue it,
I'm just
but typically no. It's far enough away to not. What makes it trans is, what you have here is, these electrons have enough association here. It's like they're bonding, and it's blocking one side. Now you can show that as a full bond, as a bromonium, or you can show it with the partial bond, like I showed you to the right on the other page. But it's enough back bonding to block one side, and the nucleophile has to come in opposite. That leads to trans. And what we say here is there's no cation form. These bridge species have actually been isolated and observed by X-ray crystallography, etc. Question here.
In your intermediate, aren't there hydrogens on the backside?
Yeah, but the hydrogen is so small it doesn't influence. It actually, it's back there. When this comes in, it kind of moves that way. We'll do more of that as we go along. You're right, though. But it doesn't influence. It gets pushed forward, more back. Other question?
Yeah, so since, like, I don't know if these are identical compounds, but the trans, would this be considered racemic or no, because the cis isn't formed?
Well, we're not quite there yet. These two trans are different.
Okay.
The two trans that were shown are enantiomers. And so what I have up there is I got one shown. The other is the enantiomer. We'll be doing that in about a week. The enantiomer is the mirror image, and it's different.
So this would be considered racemic?
Yeah, it's racemic. You got two different Carol carbons, though. It's a DL pair. That's perhaps better terminology. The handout from today, everybody get one. What color was it? Yellow? That's the outline for stereochemistry that's coming up in about, probably not Thursday, but just next week. We're starting to include stereochemistry in our alkene reactions.
So we get a 50-50 mix of those
50-50 mix, yeah. Yeah. Anytime we do enantiomers, you're going to get a mix of enantiomers in this class. Go ahead.
Is that also called a racemic mix? Is it 50-50?
Yeah, racemic pretty much means one Carol carbon. And this product has two. Is there other yellow sheets? Other yellow sheets? Could you pass those all the way up, please? If you want to see a bromonium or something, you can look up this journal article. By the way, journal articles, you have free access if you're on campus, okay? You don't need to be paying for access or anything. I should say this, you have free access to the journals that GRU has a subscription to. There are journals that GRU does not have a subscription to. Of course, there's a building over that way. It's called the library that check it out, and it can be very helpful. Okay. The next reaction. If I get the yellow sheets. You got it. Okay. So that was one. Number two is going to be addition of halogen and water. If we include water in this reaction, we get a different product. We get what's called a trans-halohydrin. Alkene, chlorine, and water. The first step here is the reaction with the halogen, because an alkene doesn't react with pure water. And the alkene reacts with the chlorine to form what intermediate? Bromonium Ion. Now we've already shown mechanism for that once or twice. Now next, you have a Cl minus. But if you have water present, it will preferentially be your nucleophile. It will attack. And usually you'll use a huge amount of water here compared to that. But anytime you see water, it's going to be a reacting nucleophile, not the chlorine. These electrons will attack. Are we going to attack left or right? This is going to pull. You're going to get partial plus here. The same place there would be if there was a cation. But we know it's really not a cation. It's back bonded. This attacks here, kicks this off. What does that give? Kick the leaving group off. Now bonded here is an oxygen with two H's plus charge. So water acted as a nucleophile, opened up the chloronium ion. At this point, something can take the H and go neutral. Well, this can take it. Leave these electrons behind. We get that product. Don't worry about that drawn up or down because there's no stereochemistry here. We'll learn when that's important, when it's not. We get this plus what? What do we form here as a byproduct? HCl, hydrogen chloride. These electrons make bond to H, these electrons there. This is called a halohydrin. Halo part because there's a halogen. Hydrin is sort of like hydrate, like there's also water there. It's also called trans-halohydrin whenever trans is relevant, like with a ring. In this example, the trans is not relevant. Question? I can't hear you.
What if you had something else better chemistry based?
I still can't hear you, can't sleep. What if there's what?
Something else better chemistry based, yes, minus and
Something else, a better conjugate base.
A better conjugate base.
Then what? You need to yell.
something that's a better conjugate base than the Cl, because I mean Cl falls under you have like HCl, right? And the Cl conjugate base wants to be stable as it is because it's only same thing for bromine. What if you had like something like NH3 that won't compare or not? Can you just
You want to include ammonia in here with this?
well, not NH3, but it's
Ammonia would react with chlorine. You'll make chloramine, and you'll kill us all.
stronger than chlorine, bromine, and iodine. Better as a conjugate base.
I mean, you could put something else in here and get a different reaction, but then it wouldn't be called a halohydrin synthesis. Right here we're doing a halohydrin, which is a halogen and water. It's going to give this, in terms of a balanced reaction, HCl. Now, if you got enough water, this is really going to be H3O plus Cl minus. But I just showed you sort of the balance, complete balanced reaction. Because we know how does HCl exist in water? H3O plus Cl minus. There's lots of variations that you can do here. Now note, you do not get this. You do not get the chlorine on this carbon and the OH there. Because, why not? Because water doesn't attack there. Water attacks over here because that's where the cation would be, if it had formed, but it's really not. But I showed you that this is pooling, you're going to get more partial plus over here. So that reaction is regioselective. Now if we do this with a ring, we can see the stereochemistry. Bromine and water, we're going to make a bromohydrin. The bromine and the OH are going to be trans. Well, I'm not going to do mechanism, but this reacts with bromine to form what? Bromonium. The bromonium can either be forward if that's forward, that methyl is back. Because that's now tetrahedral. But we can also get the other one, where the bromonium is back, and the methyl is forward. So you get both of these. How do you get both of these? The alkene is planar. Both those carbons are planar. It's walking down the road. The alkene's walking down the road, sees the bromine, attacks the bromine. As soon as I attack you, you back bond. Okay, both bonds are this way, but you could have been sitting over here. And then boom, and both bonds would have been back. It's a 50-50 chance. That's how you get these two. Now from here, we can get here. What happens next? We got water. Where does water attack? Top or bottom? Same place you're going to make a cation. Top, right? So these electrons here kick off the leaving group, but since the bromine bond is back, how does this come in? Comes in forward. This just gets kicked off. But the water comes in front. Exactly. The methyl group gets kicked back. Now if we lose an H, we just get here. All right, I'm not going to do full mechanism. Okay, question? All right, let's look at it. I wish I had like 10 fingers. Pretend this ring is planar, okay? Here's the methyl coming forward. The bromine's going back. Now, it's going back, but it's also sort of like strained, and it's also bonding back down to this other carbon, okay? All right, pretend it's bonded back down here, but all that's back. Since the bromine is back, how does the water come in? Okay, somebody bring in the water.
Go throw markers on the ground. Pay attention. Throw markers.
Come jam it right here in my hand. Here comes the nucleophile. Watch the methyl though. Jam it in my, not the colored in. Okay. Well, here we go. It's going to come in, push it on my hand. And it comes in, this gets pushed back, this gets kicked off. Let's see. Here we go. Let me do two hands.
You were so right right now.
The methyl's forward, the bromine's back. This comes in, bam. It's actually opposite of that. I wish I could. This comes in, this gets kicked off, and this comes in like this. Okay? It pushes that back. All right? As it all becomes tetrahedral. Like that. Yeah, it pushes it back. I wasn't explaining things good enough. How do we get the enantiomer? If we did it here. Because here, this is coming forward, so you would attack from the back. You push the methyl forward, it would be the enantiomer. So this gives the enantiomer. We'll do more of that. You have to just practice.
Do you need to show both mechanisms?
Do what?
Do you need to show both mechanisms when it's if you assume that
Typically the other one is just sort of just the opposite. It's the mirrored. As we do more of these, we'll do more and we'll review, and it'll. We need to just show the big idea now. As we practice and do more and more, we'll do it again and again. And okay, ones at the bottom you can do on your own. We'll look at these next time. First thing with your reactions are, okay, you got to know what you're making. So you have some terminology. Chlorine and water, what the product's going to be? Trans-hydrogen, okay? Chlorine and OH. Mechanistically, what do? I make the bromonium ion, and then water attacks where? Actually attacks the more substituted carbons. So that's where you make cation, but it's really not a cation, you do backside. And so stereochemistry, you have that outcome due to backside attack. So all your mechanistic knowledge comes in. That's just bromine, one bromine on each carbon, but how do they add? It's actually trans addition of bromine. That's why if you look under Roman numeral 1, it says trans addition of halogen. Why is it trans? Because you get the bromonium ion, and then the other bromine comes in backside, and you end up trans. ICL just has a permanent dipole to consider. Okay, so work with those a little bit, and let's move on to epoxides. An epoxide is a three-membered ring with an oxygen in the ring. This here. It's going to be analogous to the chloronium or bromonium ion, where if this was a bromine, it'd be like that. Except with bromine, the bromine had a positive charge. And thus you're really hard to isolate those. Oxygen can be neutral in this form. Because of that, we can actually isolate these as end products. Make these from alkenes by reacting them with a peroxy acid. This is a condensed formula for a peroxy acid. If that's just an OH, that's a carboxylic acid. An OO is called a peroxide. If that was an H under my hand, that would be hydrogen peroxide. But instead, it's bonded to this carbonyl. It's called a peroxy acid. Show Shown like that, shown like this. A very common specific peroxy acid is metachloroperoxybenzoic acid, MCPBA. And usually you just say that as MCPBA. It's just a specific example of that. The reactivity of your peroxy acid, two oxygens are almost like the two halogens bonded together. But here, this oxygen is bonded to the carbonyl. This oxygen pulls. That makes this being pulled. That makes this being pulled. So your end oxygen has some partial plus due to all that pulling. Your pi bond is very polarizable. That means it can be very polarized. So this oxygen can easily pull in the pi bond, just pulling everything towards it. Because that's partial plus, these electrons get excited, attack the oxygen. If we attack the oxygen, we're going to kick that one off. A lot like attacking chlorine and kicking the other one off. Where are we going to make plus at on this guy, left or right? Left. So these attack the oxygen, kick that off. So this is now bonded to the oxygen and the H, so there's an OH. And we kicked off the other oxygen, so we formed this acetate. But look at this guy. The new thing has a lone pair. So what's going to happen when the new thing has a lone pair? It's going to back bond. And that's not actually formed. Because as soon as this attacks this, what is this guy doing? It's back bonding. So this is just me drawing it in class. In real life, it doesn't form that. I just think it's good to do that. So the first intermediate is actually this here, which looks like a bromonium ion, but it's an oxygen positive. Now this is pretty much your end product. All we have to do is lose that H. The leaving group, the acetate, these electrons can take the H, these electrons move on to oxygen, gives us our final product plus the acetic acid, or the carboxylic acid. And there you go. And this can be isolated. It is a strained ring, but epoxides are known. And you typically make them by reacting an alkene with a peroxy acid, shown like that. Similar to the Bromonium Ion. Again, this can't go neutral, and so something happens here and you get a further product. This can become neutral due to loss of the H. Now you can have some here to work, and we'll also look at these next time. In terms of, what are we doing here? Well, I'll redraw this. Basically, boom, boom, boom. Used to be pi bond, but now what? We have bonds to oxygen. Right? You really have to look at, okay, what did we just do? Did everybody in here realize that that's what we just did up there? We went from alkene and now we have an oxygen bonded to both carbons? You've got to sit and say, okay, what just happened here? What bonds were just made? That's the thought process of just looking at reaction. But then stereochemistry. Well, there's not going to be much stereochemistry here. Question?
Yeah, I noticed in all these mechanisms, when you're showing the alkene, like, attacking the oxygen, is it technically attacking an electron pair? Should we technically show it, like, or no, we can just show it attacking the atom?
Well, the oxygen does have lone pairs. So you're right to question. It's attacking the atom. Even though there's lone pairs there, it's still electron for oxygen because of the dipole.
So do we show it like we serve an electron pair, or no, we just show it?
We're not attacking the electron pair of the oxygen. We're attacking more of the oxygen atom. Dichloromethane, that's just a common solvent. It's actually a solvent you're using this week in lab, right? Okay. Got to get used to seeing solvents with your reactions. By definition, the solvent is inert. It does not react. With the ring, we're going to have stereochemistry. So just like the bromonium, what type of stereochemistry did we have with it? Showed that. We're actually going to have stereochemistry here. At this point, just sort of think about the stereochemistry and let's see, give you a chance to do that, and then we'll talk about it. In terms of showing the product without stereochemistry, you're just putting an oxygen there. Next reaction we'll look at is making cyclopropanes with alkenes. Cyclopropane is a three-membered ring carbon ring, all carbons. Make this from an alkene. Essentially, you're just adding the carbon here to connect the two carbons there. These can be made two different ways. The first way is using diazomethane, which is CH2N2. Diazo meaning two nitrogens, methane, just one carbon. Diazomethane is actually a gas. It's pretty toxic. Because of that, this is not an easy reaction to do practically. Mechanistically, I've shown it to you here. Lewis structure for diazomethane would be this here. You cannot show it without showing charges. Okay, net neutral. If you heat diazomethane, heat it too much, it will explode. But if you heat it controlled, what will happen is this nitrogen positive will leave. One molecule will go to two, so that's driven by entropy. When this leaves, we create nitrogen gas. When we get this species here, which is a neutral carbon, I like to show two charges on it though, but it's net neutral. It's a carbon, here it is here. Carbon with just two H's, but it has a lone pair. Do you see that's neutral? How many electrons does it own? 2, 3, 4. Okay? It's neutral. But it doesn't have an octet. It's not a standard carbon. On day one, I showed you standard bonding. Okay? And I said if it's not standard, it will probably have a charge. Well, this is an exception. This is not standard, but it also does not have a charge. It's called a carbene. 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 Do you expect carbene to be electrophilic or nucleophilic? Why nucleophilic? It's neutral. Nucleophilic because it has a lone pair. But what about electrophilic? Does it have an octet? No. It's electron poor. It does not have an octet. So it's electrophilic. What's the hybridization of this?
sp2.
sp2 with an MTP orbital. Because if we graph the sp2, we would get 3 hybrids and a p left over. What type of bonds do you see? I see bond to H, and a lone pair. Those are going to be spread out in trigonal planar. What's left over? MTP orbital. The MTP orbital would love to have some electrons. That's why it's electrophilic. These electrons in the alkenes see the MTP orbital. Okay, walking down the road, MTP orbital. Here I come. Now, why do I show plus and minus? That's because it has dual character. The plus illustrates that it's electrophilic, but the minus illustrates that it's going to act also as a nucleophile. But it's net neutral. These electrons attack the carbon. They're really filling into this p orbital. What does that give? What does this arrow give? Bond to carbon. lone pairs left though. Carbon now is a minus charge because it owns 1, 2, 3, 4, 5. Where are we going to form plus at on the alkene, left or right? Left. Let's see, the new thing has a lone pair. So is this actually formed?
No.
No, because as soon as it's formed, what happens? Carbon back bonds, and when it back bonds, what do you get? You're done. You don't even have to remove a proton. How many intermediates in this reaction? No intermediate. Here it is. Alkene sees the carbene. Attack the carbene. As soon as I attack you, you back bond. Boom, 3-methyl ring. No intermediate. Okay? Diazomethane gives a nice cyclopropane. Question?
What's the little triangle under the
Heat. That's heat symbol. Delta heat symbol. Before we leave, let me introduce below. Another way to make carbenes is the Dichloro Carbine. This is going to give a cyclopropane with 2 chlorines. This one's much easier to make because it's not a toxic gas. It uses chloroform and base. Chloroform is slightly acidic. With the base, it takes off the H. You can look through this. We get to this point. At this point, it's analogous to up there. Chlorine leaves. When it leaves, we get the dichlorocarbene. From there, we get the chemistry takes place, and you have 2 chlorines. This is just much easier to do. We'll look at this next time. Please predict products. But please also look ahead. Any more reactions on the outline, including like with mercury, boron, mercury and boron reagents? Questions?